So today we are going to work some more on oxidation reduction. You may remember that last class we talked about assigning oxidation numbers. The most important thing to remember is if it's a pure element, the oxidation number is 0. If it's an ion, the oxidation numbers will add up to the charge on the ion. And the one that kind of dictates everything else, the highest in the hierarchy of oxidation reduction, is oxygen. And in a compound, oxygen is -2 99% of the time. And you will use it to figure out the oxidation number of other elements in that compound. So we practiced that last class. Before we start this, make sure that you know what you're doing with the oxidation reduction numbers that you assign. But today we're going to talk about how you actually use those oxidation numbers to figure out where electrons are moving in oxidation reduction reactions. So let me go to so when you have an oxidation reduction reaction, the first thing you do is assign oxidation numbers, but then you actually split the reaction into its half reactions. And usually one of them will show that there is an element that is gaining electrons and one that is losing electrons. So what the heck do we mean by this? Well, let's look at some of the examples that we have on the redox sheet here. Let's look at number 4. So if you look at number 4 here, I'm going to actually copy that onto a sheet of paper, and we're going to show how you can look at the oxidation numbers and then figure out, actually I think I'm going to start with this one because it's a little more straightforward, and we can figure out what the half reactions are and what's happening with the electrons. So my first one that we're going to look at, let me take this down to a partial screen and start sharing my document camera instead. So the first one we're going to look at is this one. Manganese 2+ plus bismuth 4 hydroxide goes to permanganate and bismuth 3+. Okay, so the first thing we want to do is assign oxidation numbers. So manganese is just an ion by itself, so it's +2 on this side. And manganese over here, well, oxygen, I've got 4 -2s, so that would be -8. So in order to get back to -1, this manganese must have an oxidation number of +7. So you can see how manganese went from +2 to +7. Let's look at bismuth now. Let me see, tilt this just a little. So for bismuth, if this 2 oxygens would be -2 apiece, so -4. So this bismuth is +4. And then of course this bismuth is +3 because it's just an ion by itself. So now I'm going to split these into half reactions. So one of my half reactions is the one where manganese is losing electrons. Why do I say it's losing electrons? Well, it's getting more positive. And then my other half reaction is my half reaction with bismuth. Bismuth is gaining electrons. Why do I say that? Well, it's getting less positive. The first kind of oxidation reduction reaction we're going to work is called an oxidation reduction reaction that happens in acid. You'll explain what that, I'll explain a little bit more about what that means later. But the first thing that you do is you make sure that your primary atoms are balanced. In other words, I've got one manganese on this side, one manganese on that side, one bismuth, one bismuth. So those are good. So how do I balance the oxygens? Well, in oxidation reduction reactions, you balance the oxygens by adding waters to the opposite side. So for example, here I have 4 oxygens, so I'm going to add 4 waters to this side. Now I've got 4 oxygens and 4 oxygens. So what will I have to do on this side? Well, I'll have to add waters to the side without any oxygen. Oops. Yeah. So I have 2 oxygens, so I'll need 2 waters. The problem is, once I add those waters, I now have extra hydrogens. So after you've added the waters, you now add H pluses, like you have in acids, to balance out the hydrogens. So 4 times 2, I have 8 hydrogens. So I'll add 8 hydrogens to that side to balance it. And then on this one, I've got 4 hydrogens. So I'll have to add 4 hydrogens to this side to balance it. So just to reiterate, I now have 4 times 2, 8 hydrogens, and 8 hydrogens. 4 times 1 oxygen, 4 oxygens and 4 oxygens, and 1 manganese on each side. Here I had a bismuth on each side, 2 oxygens there, 2 oxygens there, 4 hydrogens and 4 hydrogens. So my half reactions are now balanced. So the thing I need to look at next before I try to put them back together is how many electrons moved. And so the way we figure that out is by looking at my 2 oxidation numbers. So electrons are negative. So what I would have to do to balance my +2 to +7 is a -5 on this side would make my oxidation numbers equal out to both +2. So you always add electrons to the side that has a more positive oxidation number. So this is +2, this is +7. If each electron is -1, how many electrons will I need? I'll need 5, right? If I add 5 electrons here, the 5 electrons are negative, so 5 negative ones, you add that to the +7, I'm at +2, which is what I need my oxidation numbers to equal out to. Over here, it's a little easier, right? This one's +4, this one's +3, so I need to add, sorry, I always do this to run out of space. I need to add 1 electron to that side because the 1 electron plus the added to the +4 makes this side +3, which equals the +3 there. The reason that we're showing it that way is because ultimately what happened is an electron joined to this to get to +3. What happened here is that 5 electrons were lost in order to get to the +7. So we show that the 5 electrons have separated off. Now the reason that matters is that in order to balance these, the half reactions have to show the electrons canceling out. In other words, if this one is losing 5 electrons, they have to go somewhere. Electrons don't just move without provocation. So they're going to have to be absorbed by this half reaction. So the last thing that we do is we multiply the half reactions in order to get the electrons to cancel. You notice I have 5 electrons on the right here. I need this one to have 5 electrons on the left. Think about it. You've never seen a chemical reaction that shows electrons. That's because the way that they react is in such a way to cause the electrons to cancel out. So I'm going to need to multiply this half reaction by 5. So when I do that, I will now have 5 electrons plus 20 hydrogens plus 5 bismuth 4 oxides going to 5 bismuths and 10 waters. Now I can actually recombine my 2 half reactions to get 1 mammoth reaction. So let's see what that would look like. On the left, I'm going to have 4 waters plus manganese plus, now I'm not going to write my electrons because they will cancel, plus 20 hydrogens, plus 5 bismuth oxides. That's everything on the left, right? That. And then on the right, I'm going to have my manganese, my permanganate plus 8 hydrogens plus 5 bismuths plus 10 waters. Now, one thing you'll notice at this point is that I've got waters on both sides and hydrogen ions on both sides. So I'm going to want to cancel those out. So what I can do is I can subtract 4 waters from each side. That'll get rid of the waters here, and that'll make this one, when I subtract 10 minus 4, this one's at 6. And then here, I'm going to subtract 8 hydrogens from each side. So I'm going to subtract those, and then 20 minus 8 is 12. So my final reaction is Mn2 plus 12 hydrogens plus 5 bismuth 4 hydroxides go to a permanganate plus 5 bismuths plus 6 waters. And it's always good to go back and double check that your elements balance out. So I've got 1 manganese, 12 hydrogens, 6 times 2, 12 hydrogens, 5 bismuths, 10 oxygens, and I've got 6 oxygens here plus 4 more there, 10 oxygens. And that is a balanced oxidation reduction reaction. So let's go ahead and kind of let you start by trying one that's a little simpler. I'm going to try the first one on the back of redox number 2 on the right. That's going to be, let me get this down so I can see what you're seeing. That is going to be the Fe2 plus and ClO3 1 minus going to Fe3 plus and Cl1 minus. So pause this for a second and see if you can assign oxidation numbers. I'm assuming you paused it and now you're back. The oxidation numbers you should have had are this iron is +2 and this iron is +3. That one's super straightforward since they're just irons. This chlorine is -1. This chlorine, let's see, 3 -2s would be -6. So this chlorine has to be +5 in order to get to end up at -1. So see if you can now separate this into half reactions. You may want to pause this for a sec. So once you have separated into half reactions, hopefully you did it this way. Iron 2 plus going to iron 3 plus, and then chlorate going to the chloride ion. Notice that even though oxygen does have an oxidation number, because it didn't change, I'm not worrying about it. I'm just leaving it. Because you're really only focusing on thinking about the oxidation numbers of what's changing. So this first one is super easy to balance, right? We've got 1 iron 2 plus, 1 iron 3 plus. So think for a second, which side are we going to add the electron to? Well, in this scenario, this is +2 +3. So if I add a negative electron to this side, then +3 and -1 are +2. So now my oxidation numbers are balanced. This one is +5 and -1. So I'm going to have to add 6 electrons on this side because this, remember, electrons are negative, so this would be the equivalent of -6, and +5 gives us -1. Sorry if that 5 is not horribly legible. So remember, this side is done, right? We just had irons, they're balanced. So how do we balance oxygens again? By adding waters to the flip side. So I'm going to add 3 waters here, and I'm going to add, now I'll balance the hydrogens by adding 6 hydrogens here. So take a second and look at that and make sure it all makes sense. My chlorines were already balanced. To get my oxygens to 3 on the flip side, I added 3 waters. Then because I added waters, I now have hydrogens, so I added 6 hydrogens to the left. So the last thing we have to do is to consider how we're going to have to multiply our half reactions to get our electrons to balance out. One really good kind of intermediate way to check your work is you do always want to make sure your electrons are on opposite sides. If somehow you have electrons that are both on the product side or both on the reactant side, it means that you misplaced your electrons. They have to be on flip sides. So here you see it's on the product side, and then on this half reaction, it's on the reactant side. So all we have to do to finish this is I need to get this up to 6 electrons, so it'll cancel out those. So I'll multiply this half reaction by 6. So this would be 6Fe2 plus going to 6Fe3 plus 6 electrons. So now I'm ready to put it together. So I've got my 6 iron 2 pluses and my 6 hydrogen ions and my chlorate ion going to 6 iron 3 pluses plus chloride ion and 3 waters because my electrons canceled out. So just double checking, I've got 6 irons, 6 hydrogens, 1 chlorine, 3 oxygens, and 3 oxygens. Balanced. Bam. So I'd like you to go ahead and try, let me share a different page for a second. I'd like you to go ahead and try to do number 2 next, and on your own, and then I will show you the answer. I hope this has been informational, and we'll work some more of these together in class.